All right, what's good, y'all? Mr. Love here, back at y'all with another video. This video is going to be an AP Calculus refresher. So if you've taken AP Calculus AB and you're going to BC, or maybe you're going to college and you just need a refresher on some calc topics, we're just going to go through some problems in this video, going over limits, derivatives, integrals, kind of the whole shebang. All right, so I got 4 problems for y'all. So let's just jump into it and give them a go. So problem number 1, we have a function f that we're told is twice differentiable, and we're told that f double prime of x is less than 0 for all x. The graph of y equals s of x is the secant line passing through the points 2 comma f of 2 and 6 comma f of 6. The graph of y equals t of x is the line tangent to the graph of f at x equals 4. Which of the following is true? So they're giving me this ordering of values for f, t, and s. So for a question like this, they're talking about tangent lines and secant lines. I love sketching a graph. So I'm gonna go ahead and do a little sketch. So the points in question, we have x equals 2 and x equals 6. So I'm gonna go ahead and just make a little tick mark at 2 and 6. And then we also have a tangent line at x equals 4. So I'll put 4 right here in the middle. And this function f, we're told, is f double prime of x is less than 0 for all x. So that tells me that f is concave down, because the second derivative tells me about concavity. So I'm going to go ahead and sketch the graph of f on this interval. So it's going to be a concave down graph. So something like that. And it says s of x is the secant line connecting the points 2 and 6. Okay, so at 2 and 6, if I make 2 points here, s of x will be the secant line through those 2 points. So I'll label that s of x as my pink graph. And then t of x is the line tangent to the graph of f at x equals 4. So right here at x equals 4, I have another line, t of x, would be my green line, that is tangent to the graph of f, which is my purple graph. All right, so I got f, I got s, I got t. Which of the following is true? So they're talking about these function values at 4.3. So 4.3 would just be slightly bigger than 4, so slightly to the right of 4. So I'm just pretty much trying to figure out which of these values is biggest, middle, and smallest. So if I go up to these graphs, I can see that my green graph, which is t of x, is the largest, and then it goes purple, and then it goes pink. So if I'm going small to big, the smallest one is s. So s of 4.3 is the smallest. And then it is f is in the middle. And then the biggest value is t. So I want s, then f, then t. S, F, T, yep. So that's going to be choice C. So the crucial part for this question was just making your sketch, sketching the curve, the tangent line, the secant line, and then just being really precise with how you draw it so you can really visually see it. So, cool. Not too crazy, hopefully. All right, on to number 2. So this time we have an integral. So we have an indefinite integral of 1 over t squared times the square root of t dt. So off rip, I look at this denominator, I see t squared and I see root t. I'm gonna rewrite that and clean that up a little bit. So I know that t squared, just focusing on the denominator real quick. So t squared times root t. Root t is the same thing as t to the 1/2. So I can write that as t squared times t to the 1/2. And then I multiply these exponents, I have to add my powers. So I'm adding 2 plus 1/2, which you gotta be good with fractions at this point in your math career. I get 5 halves. So this is t to the 5 halves. So now I can rewrite my integrand as 1 over t to the 5 halves dt. But now I'm going to do one more step to just try to make this, a little bit more integrable. That is a word. 1 over a power means you can make the power negative. So I can rewrite this as the integral of t to the negative 5 halves dt. So now at this point, this is pretty much just reverse power rule. We take the power negative 5 halves, add 1 to the power, and then divide by the new power. So we're going to have, if I take negative 5 halves and add 1, that's negative 5 halves plus 2 halves, which is just negative 3 halves. So when I integrate, I get t to the negative 3 halves divided by negative 3 halves. And then don't forget your plus c. Now, dividing by negative 3 halves is the same thing as multiplying by the reciprocal of negative 3 halves. The reciprocal is going to be negative 2/3. So I have negative 2/3 times t to the negative 3 halves plus c. Go ahead and box that. Is that an answer choice? Yes. So we're going to go here with choice A. All right, so exponent properties, reverse power rule, that's it. All right, number 3, we have a definite integral this time since we have bounds here. So we have the integral from 0 to 4 of the square root of 4 minus x over 4 dx. All right, so there's a lot of different ways you can go on this one. My mind normally jumps to, if it's not one of my basic rules that I know, like reverse power rule or derivative of a sine or a cosine or e to the x, it's probably going to be a u sub. So I want to probably do a u sub by picking this inside of my radical to be u. But I'm going to first rewrite this so it's cleaner for me to work with when I do the u sub. So I'm going to write this as the integral from 0 to 4 of the square root. I have a single term denominator, so I can break my fraction up. So this is going to be 4 over 4 minus x over 4 dx. Now 4 over 4 is just 1, so this is going to be integral 0 to 4 square root 1 minus, dividing by 4 is the same thing as multiplying by the reciprocal, or 1 over 4. So I can write this as 1/4 x dx. Now I can see that my u clearly is going to be this inside, right? So 1 minus 1/4 x. So that's going to be my u. So now differentiating both sides, I get that du equals negative 1/4 dx. Derivative of 1 is 0. Derivative of negative 1/4 x is negative 1/4. All right, cool. So then now I want to replace everything in my integral that has an x or a dx in terms of u and du. So I got my u accounted for. Now I got to solve for dx. So I'm going to divide both sides by negative 1/4. Or if you want to think about multiplying both sides by negative 4, tomato, tomato, what we get is negative 4 du equals dx. All right, so my dx is good. The thing that kids forget sometimes when they're doing u sub with a definite integral is you got to change these bounds. All right, students forget that sometimes. So I need, these bounds are in terms of x. I need them in terms of u. So I'm going to use my definition of u, 1 minus 1/4 x, to find those u bounds. So I'm going to say u of 4. I'm going to plug 4 in for x. So 1 minus 1/4 times 4. 1/4 times 4 is just 1. 1 minus 1 is just going to be 0. And then u of 0, I have 1 minus 1/4 times 0. 1/4 times 0 was 0. 1 minus 0 was 1. All right, cool. So now I'm ready to rock. So rewriting this integral, I have the integral going from 0 became 1 and 4 became 0. The square root of my inside is u. And then dx is -4 du. All right, cool. So everything's in terms of u now. So then now this constant of -4, we can move to the outside of the integral. So we're going to have -4 times the integral from 1 to 0. And now I'm just going to go ahead and rewrite the square root of u as u to the 1/2. Just setting myself up to integrate. And so at this point, you can just integrate here. I also noticed that these bounds go from like bigger number to smaller number. So, I mean, you could do it this way, but if you're not comfortable with that, you could just switch the bounds and just put a negative out front. So what that does actually is it gets rid of this negative that's out here. So we're just left with +4 times the integral from 0 to 1 of u to the 1/2 du. And so then now we can just do reverse power rule on this. So add 1 to the power. 1/2 plus 1 is 3/2 last time I checked. So u to the 3/2. And then divide by 3/2. Divided by 3/2 is the same thing as multiplying by 2/3. Let me scooch this down a little bit. All right, and then I'm integrating or evaluating from 0 to 1. And then let's not forget that 4 right there. Okay, cool. So then now I just use fundamental theorem, plug in my top bound of 1 for u, minus plug in my bottom bound of 0. So 1 to anything is just 1. 0 to the 3/2 is 0. So I'm going to get 4 times, this is just going to be 2/3. And then 4 times 2/3 is going to be 8/3. So we're going to go here with choice B. So when you're doing U-sub, just remember, change your bounds. If you have a definite integral, change your bounds and work in terms of u. All right. Bet. All right, we got one more. This one is limits. Okay, so let's see. They gave us some Roman numerals. 3 limits. Which of the following limits are equal to -1? Okay, so we pretty much just need to analyze these limits separately. So I'm going to go with the first limit to start. So they have the limit as x approaches 0 from the left. Sneaky little negative sign. So 0 from the left of x divided by the absolute value of x. So this is a one-sided limit. And anytime I get a one-sided limit, what I typically do is try to think of a number that's really, really close to that number from whatever side we're coming from. So if we're approaching 0 from the left, I need to think about, okay, let me pick a number really, really close to 0 from the left. So it's going to be like something that's like negative, but close to 0. So I'm thinking like -0.01, like something real small. So to start, we're going to let x equal -0.01. So I'm trying to figure out what's this expression here doing as we get close to 0 from the left. So for values really, really close to 0 from the left. So if I plug in like -0.01 into this expression, if we simplify this, we get -0.01 in the numerator, and the denominator is just +0.01. So I have the same thing pretty much except for this negative sign. So this is just going to reduce to -1. So we're approaching -1 as we approach 0 from the left. And so number 1 checks out. That limit is -1. All right. Roman numeral 2, we have the limit as x approaches 4 of this rational function. So again, off rip, I see a quadratic, so that's screaming at me that I need to factor. So I'm gonna go ahead and just factor this. So this is gonna be, let me switch colors. The limit as x approaches 4. In the numerator, I'm gonna factor this. This is gonna be two numbers that multiply to 20 add to -9, so -4, -5. So x minus 4 and x minus 5. And then in the denominator, I have 4 minus x. Now, usually when you factor, you can cancel stuff. I want to cancel the x minus 4 and this 4 minus x, but I can't cancel them because they're not exactly the same just yet. I noticed that the 4 and the minus x are kind of just swapped around. I really want an x minus 4. I don't want a 4 minus x. So a slick way to kind of get around that and force that is to actually factor out a negative. So sidebar, I'm probably going to erase this in a second. Actually, I can probably zoom out. So sidebar, 4 minus x. If I factor a negative out, so let me write it like this. If I put the x first, it'll be negative x plus 4. Since this leading coefficient here is negative, if I factor that out, I'll get negative, and then in parentheses, x minus 4. Notice that if I distribute this negative back, I get a negative x and a positive 4, which is what I started with. So I actually can rewrite 4 minus x as negative, and then in parentheses, x minus 4. So slick way to do that. Now, I can see that I can cancel x minus 4 top and bottom because I'm multiplying. So those are gone. So now we just have the limit as x approaches 4 of x minus 5. And then in the denominator, all we have left is just a -1. All right, so now I can just do direct substitution. So plugging in 4 for x, we get 4 minus 5 over -1, which is -1 over -1, which is actually +1. But I want -1, so this one is out. All right, Roman numeral 3. We have the limit as x approaches positive infinity of another rational function, 2 minus x over 2 plus x. So again, different ways you could do this. You can think about, growth rates. You can think about the highest power of x and horizontal asymptotes and things like that. Anytime you have a limit to infinity or negative infinity, that's pretty much the same thing as finding the horizontal asymptote. So in pre-calc, we did that. But I'm gonna show you a different way to kind of analyze this too. So notice that the 2's are constants. So out to infinity, those are not going to be really as powerful as x, because x grows really, really fast compared to a constant, right? Constant just stays the same. So what I can actually do here is I can actually divide everything through by the highest power of x, all right? So the highest power of x here is x to the first. So if I divide everything through by the highest power of x, we get the limit as x approaches infinity of 2 over x minus x over x divided by 2 over x plus x over x. All right, so then now simplifying this, I get limit as x approaches positive infinity of 2 over x minus 1 in the numerator over 2 over x plus 1 in the denominator. Well, now at this point, I'm like, okay, cool. So as x goes to infinity, like x gets really, really big, like 100, 1,000, 1,000,000, 2 over x, 2 just stays as 2. So think about like if you have 2 over 100, 2 over 1,000, 2 over 1,000,000, those numbers are getting really, really small as x gets really, really big. So 2 over x just approaches 0 as x approaches positive infinity. So this expression is going to be 0 minus 1 over 0 plus 1. And then negative 1 over positive 1 is just negative 1. So 3 checks out. So it looks like the only options here are 1 and 3 that are true. So I'm going to go with choice C. All right. So yeah, that was a good question. It gave us different ways of evaluating limits, right? We had one-sided limits, limits by factoring, limits at infinity. Pretty good mix. All right, cool. So that's the 4-piece. Let me know what other topics y'all would want me to go over. I'll be posting more videos on these topics as well. So appreciate y'all watching. All right, like, follow, subscribe, send this to a friend, send this to a homie, all of that. All right, and I'll catch y'all in the next video.